So I met Katie through the Great Traveler process actually here, and it was really awesome to hear her talk, and I wanted to let her talk today. So Katie Edwards.
So I kind of steal my thunder on my side, but anyways, today I'm going to be talking to you guys about an ensemble model for detecting malware callouts in real-time network traffic, and this is a project that my team has been working on in Capital One, and we have in production right now, and it's just I think it's a really cool project. Like I mentioned, I was part of the technology development program at Capital One, so I did a couple rotations in different roles. In my previous, or the last one in my program was in our information security and risk management group. So I was working in our security intelligence center. Always have been interested in cybersecurity, and then I made a switch about 7 months ago over to our Center for Machine Learning group, and they're working on a pretty large use case in the cybersecurity realm at Capital One, so that was really cool for me. So I'm going to tell you a little bit about one of our models. But to start out, how does malware get into a network? We obviously, as big corporations, have a lot of security in place to try and stop these things. But most of the time, it's as simple as just visiting, a website that's been corrupted. We see some stuff getting through phishing emails, which are surprisingly hard to detect what's phishing and what's not. And so, employers will get phishing emails with malicious links in them, or sometimes even just the malware is attached in the email and they don't connect data. And so it's pretty simple, but that's how your computer can get affected by malware. And essentially, a lot of times what happens is these computers are then used to form a botnet, which is essentially just a network of compromised computers that all reach out back to a central command and control server to wait for additional action, sometimes to exfiltrate data. Oftentimes, malicious hackers will use that network of computers to initiate denial of service attacks. So they can really be used in any number of ways, but kind of at the mercy of these command and control servers. So kind of looking at the history of some of this malware, we see all the way back in 2008, things like Torping and Conficker that, Conficker infected anywhere between like 9 and 15 million computers. And, we have now CryptoLocker and Game Over Zeus in 2013, and as recently as 2016, things like Locky that are infecting millions of computers. And the commonality between a lot of these is that they're all, again, calling back to a central command and control server. So the question is, how does this malware reach those servers? In earlier malware, essentially what would happen was the hackers would hard code the domains into the malware binaries. And then once that malware was executed, it would attempt to reach out to those different domains until it found one that bound to that command and control server. But obviously, as we've become more sophisticated on the security side, it's pretty easy to just block those domains that we find in malware binaries and stop those from calling out. So newer malware leverages something called DGA, which is a domain generation algorithm. And essentially what that does is it automatically generates new domains on the fly, so that prevents you from being able to, take down those command and control servers really easily. And these were popularized first by Conficker. The earliest versions were only producing about 250 domains per day, but now the latest versions are producing, over 50,000 domains per day. A small subset of these domains, maybe less than 1%, actually map to an actual command and control server. But you'll see it calling out to all those domains, and it's really hard for a security analyst to determine which ones of those are the command and control servers, to distinguish between malicious domains and legitimate ones. So this is a really popular method that malware uses. So it's really difficult to defend against. Especially at a company like Capital One, where we are in our current cybersecurity data pipeline processing about 70,000 events per second. So if you can imagine, all 40,000 employees at Capital One constantly reaching out to the internet, and we have to process every single one of those requests, trying to figure out if it's going to a malicious domain. Short of hiring 70,000 security analysts, that's really not going to be possible. And if we have malware that is producing 50,000 reverse engineer the malware. In the earlier days, those domains would be hard-coded into the malware binaries. And now the domain generation algorithms are hard-coded in, so you can reverse engineer the domain generation algorithms and then try and get the list of all 50,000 domains that that particular piece of malware might be calling out to. But usually they're time-seeded and they change really quickly, so that's still difficult to keep up with. Another solution that many people use is to use DNS data to proactively predict when a server or a hacked computer is calling out to a CNC domain. And so essentially the way it does this is it looks for callouts to non-existent domains. So obviously domain names have to be registered, and you can compare domains that are appearing in your network traffic to a list of existing domains that are registered and say, okay, maybe this person called out to one non-existent domain, they may have just fat figured that URL, but if a particular user is calling out to thousands of non-existent domains in just a few minutes, that's a really good indication that it's a DGA algorithm and it's trying to reach out to a command and control server. So this is a great solution, but there are a lot of reasons why it doesn't work for us and many companies. Capital One and a lot of other large organizations acquired different companies throughout its lifetime. And so we have a pretty disjoint infrastructure from all of these acquisitions. So collecting DNS data is not trivial. It's a really difficult process. And that's something we just don't have a process for doing a holistic collection of DNS data right now. So we were trying to come up with another solution to this. So what do DGA domains look like? On the left are some domains that were generated by DGA algorithms that we have reverse engineered. On the right are some domains that you guys know very well. And obviously when you look at these domains on the left, you in your head can immediately recognize, like, this is not right. This is not a usual domain. The whole point of domain names is so that they can be remembered by humans easily, so we don't have to remember IP addresses. So obviously having domains like this doesn't make any sense. But it is difficult to describe why we know that this is malicious, right? You say, okay, I can't say it out loud, I can't really read it. Maybe there aren't quite enough vowels in between all the different consonants, or there are too many consonants. But to kind of come up with that logic is a difficult process, which is why it's a great use case for machine learning. So again, we look at the domain names, we analyze the text, and we, all in our head determine whether it's suspicious. So is it phonetically plausible? And then even on Facebook, we look and say, do the words make sense together? Maybe, 15 years ago, Facebook might not have sounded right to you, but obviously now that's something that everyone knows well and good. But looking for words that just don't really make sense together in that domain are also a way that we recognize that it might be suspicious. But so from this, we kind of thought, okay, well, this is the way humans process it. So we're definitely going to go with a linguistic model to try and solve this problem. So we essentially looked at it from the perspective of trying to analyze that domain in regards to language. Now talking about what features we use. All we have to look at is this small string, which is the second level domain name. So what kind of features could we possibly extract from maybe a 10-character string? And surprisingly, you can actually extract a lot of features from this. We look at things like the vowel ratio, the digits ratio, the distinct character ratio. We look at every possible substring in that string and compare it to a dictionary and say, are there real English words that exist within this string somewhere? And get that ratio. We use n-gram-based features, things like that. So we actually were able to extract over 50 domains from just these small character strings, which is pretty surprising. Obviously, machine learning is iterative, and we ended up throwing away a lot of these features that just didn't really help us anyway. But we ended up with a little over 20 features for our final model. And then where do we get this training data for our model? For the DGA domains, we reverse engineered the domain generation algorithms from over 60 different malware families, and then generated those malicious domains and used that as our negative training data, and then we use the Alexa 1 million list that has essentially a list of 1 million legitimate domains And then we used a random forest as a model for this. There were obviously a lot of initial challenges. Like I said, machine learning is a very iterative process. And so the first thing that we immediately ran into was we were getting a pretty high number of false positives on this. And that reason was that Capital One is a multicultural organization. We have employees that, like tons of employees that speak English as their second language. And so during the workday, a lot of these people are going out to domains that are have been transliterated from other character-based languages or any other language into English. So almost all of the research that's been done on DGA has been in the Latin and Germanic-based languages space. So that was a huge issue that we ran into right off the bat. So obviously, as a human, if we only know English, looking at any other language that will look like gibberish to us, it's the same thing for computers. So that was the first problem we ran into. And so again, this transliteration. You might look at this domain name here, Ghana.com, and think, okay, I've never in the English language seen, two A's show up in a row. That's not a word that I recognize or understand. Even though it is phonetically plausible, I can pronounce it out loud. But that's actually the transliterated word song from Hindi into English, I guess, or into the Latin alphabet. So they're often transliterated from other languages. But the main issue here is that there isn't a lot of dictionaries for these other languages. So Pinyin is one of the only publicly available ones, which is the standard Chinese translated into the Latin alphabet. So we have Pinyin, but we don't really have any other dictionaries publicly available for different languages. So we started to create these transliterated dictionaries from other languages and are feeding that data into our random forest as well. This is not something we've finished by any means. That's like a huge undertaking to create these transliterated dictionaries for every single language, but we do have two of them done and something we'd like to continue to work on when we get more time. But so, as you can imagine, that's great for those DGAs that I showed you before, where you're getting a string of just random characters and numbers in no particular order. Another type of DGA that I didn't mention that proves to be a big challenge for us was dictionary DGAs. And in dictionary DGAs, what they do is they will just take a random combination of words from a dictionary and put those together into a domain name. And so that's difficult because they are complying to most of the language rules. They're obviously phonetically plausible, and we do that, like we were saying, looking at the substrings and doing a dictionary lookup, it's going to pass our original model. So how do we handle this use case? Okay, again, dictionary DGAs, they will combine words that are random. Like I said, Facebook might have seemed random in the past, but now we're all pretty used to it. But things like Ford, Apple, or like, I don't know, you put Ford, Apple, like domain name, and that would be kind of suspicious to us because not something we usually see in normal language. So what we did was we capitalized on this randomness and built an additional collocation model. We didn't exactly use word2vec, but we used something similar that essentially gives us a score on the likelihood of two words occurring in the same sentence or paragraph. And then we combined that collocation model with our random forest model to create this ensemble model. And so that's the model that you're going to see here. So we have our training data set that I mentioned we got from reverse engineering with DBAs and from the Alexa 1 million. We have a corpus of dictionaries in the English language. We took the dictionaries from other native languages, we transliterated them, and then we combined both of those models and normalized them into a single score, which we have running in our big data pipeline for our information security and risk management group. So this is one that we're really proud of. It's been in production for about 6 months, and so far we have had no downtime on our model server. So the next part that I'm going to talk to you about is more of the data engineering side, which is also a really interesting challenge when you're trying to deploy machine learning models at scale in a production environment like Capital One's. So as I mentioned before, our training data set is pretty big. And then in itself, the natural language processing that we did on this data is pretty computationally expensive. So all of the code had to be written with distributed processing in mind. Our data pipeline, which I'm gonna show you a diagram of in a minute, is processing 5 terabytes of cybersecurity data per day. We get about 30 different log sources. We have a few in particular that we use for like our web proxy traffic when we're getting these domain names. But overall in that cybersecurity data pipeline, it's about 3 billion events per day and 70,000 events per second at peak processing. So our model server, and I think it's about 30,000 events per second just for our model server. So that's just pure people reaching out to the internet going through our web proxy. So our servers have to be able to process and give a score back at 30,000 events per second. And then we have to extract the features from that domain in real time. So this is what our data pipeline looks like. We kind of have a separate server where the information security risk management group pushes us the data from all the different log sources. They're fed in through NiFi and then into our streaming data platform where they're parsed. So we had to parse all of these different log sources. And then this is kind of where the machine learning part comes in. So we have in this data pipeline what we call an enrichment vault. And so in this enrichment vault is where we're adding on to our data contextual information. So we'll just add, if the log contains an IP address, we'll add in geolocation data. We have, a few other different types of enrichment vaults, but the big one here that we're using for that proxy data is our domain generation algorithm score. So what we do is we have our models running on a bunch of gRPC servers and then in the cloud, and then we have an elastic load balancer that helps us distribute those 30,000 events per second to all of our different model servers. So that has been kind of one of the key components in allowing us to, one, have this model server up and running for the last 6 months of the downtime, and to be able to process all of that in real time. So it's separated out from the pipeline, so any changes we make for our model server don't affect the rest of the pipeline. And because we're running it in the cloud on this distributed system, we can push changes without affecting essentially the whole pipeline. We can spin up basically 5 extra servers where we push changes to that model server and let the load balancer distribute it to those other 5 servers and then take down the old ones so that we don't have to downtime there. This is kind of what I mentioned here. So we've essentially created this machine learning as a service. And then to talk about, which I probably could have mentioned earlier before I went to the data engineering side, we have this massive cybersecurity data pipeline. And like I said, about 70,000 events per second. And we have a team of analysts in our Security Intelligence Center. I'd say there's about 20 of them there at all times. They're a 24/7 group. And they're the ones that are responsible for when we generate these alerts for processing them. So one of the big issues here that we were concerned with was not only having really good accuracy, but also making sure that we keep our false negative and false positive rates down. Because we have a high false positive rates and we're giving them thousands of events, just even during the day, so then the process actually too much. So when you're thinking about developing machine learning models at scale in this type of use case, we really need to keep those low. Because I used to work in the SIC and I know that they would kill me if I started sending them 1,000 events per day. But our overall accuracy for our model is at about 99.7%. I don't have the numbers for our false positive rates, but they're really low. I know that they haven't been able to they're really happy with how it's turned out. But when we spun this up within the first week of it being, or the first day of it being in production, we caught already like 5 different domains that were malicious that the current cybersecurity applications that we use at Capital One weren't able to catch. So day one we were catching stuff that we hadn't seen before, so that was really exciting for us. And yeah, we were able to actively detect the production pretty quickly.
you do with the information that you found a DGA? And I'm sure that that's a step beyond perhaps your pipeline, so I'm curious to know if you go back and then the person knows where it came from and how to deal with it.
Yeah, so we have a team of analysts that we generate alerts off of this, and those go to our security intelligence center. So this platform was developed for them, so they're not just getting alerts for like our web proxy, but they get alerts for basically every security event that goes on in Capital One. And so they would investigate this, and I think the first step would be to block that domain. So to make sure that the infected machine can't call out to that command and control server. And then the next step is we have a forensics team that would then go and confiscate that laptop, make sure that, if they were compromised, the data wasn't being exfiltrated from Capital One, and then also to do cleanup on it and remove that malware before getting it back to the employees. And I think it also would just allow us to, so what we can do is if we do recognize a domain that was DGA generated, we can also then go look in our proxy logs and look at every single machine in our network that has tried to call out to that particular domain and do the same thing for all of those. So we can really, at that point, see how far the malware has spread, and whether any data was lost because of that. So we do have a couple of pieces in place on the security side that work with that. Yes.
I'm pretty sure I was looking at it, you said you have 1 terabyte at the end of the day?
5 terabytes of data per day.
Okay, so is this all like network packets? Basically, what type of data do you get?
Yes, we have I think we have right now, we have more than this, but right now our pipeline is processing, I think, 36 different security applications. So we look at everything from, firewall logs, web proxy logs, we have full ECAP data, email logs, and then just, for all of the employees, things about their machines that, track any suspicious activity. We have things looking for, PII being sent out of the network. So it's a little over 35 separate security appliances that we get those logs from. And then we work to, combine some of that data into one generated alert so that we can kind of, not one for everything, but when I used to work in the SIC before we had this kind of generalized platform, we were having to log into each of these different applications ourselves. So, during a given day, I was logging into like 16 different security tools to try and investigate this one incident. And so our goal here is to have it all in one place and kind of have a single pane of glass where we can, if we get an event like this, then what I can do is look in our email data and say, okay, did this come from an email to this person's computer? And then say, okay, who is this email sent from? And then look up every single person in the company that received this email from the same person. And so we basically, with this platform, have created a single pane of glass for that, where we're able to pull all those logs into one place, so that we basically sort of stitch that context together for our analysts. Yeah, no problem.
Since you were gathering data from different types of logs, will you have problem with generating extracting features because there are different types of logs data on the podcast?
So for us, this model, so we have yes, it's a separate group that I do spend some time with that is responsible for that data pipeline and parsing all the data for different logs. Our model server in particular is just getting the domain, so once it's parsed out, we only get that domain string essentially.
You're not doing all those features to all those servers?
Not in this particular one. We are generating other alerts off of it, so it goes through the pipeline that I mentioned here. We are just a kind of a piece of this, and then there are other enrichments that we add on, but we have, essentially, it goes into Elastic, Search and Elastalert, and then there are alerts generated off of that. So there are other alerts set up in place besides just the one for our DGA. This DGA was the first machine learning portion that we had in this pipeline. We are looking at incorporating more and working on other projects for the cybersecurity group in general. Although our group does do machine learning projects for other lines of business as well. So this is our first main customer, and kind of my favorite piece of it, but we do other projects. Yes.
So that you guys thought about incorporating a database model for the DNS?
In terms of, for DNS, We haven't, so because of the kind of complexity of Capital One's network, we haven't really looked too much into, because we can't really do DNS data collection, we haven't looked at that side yet, so we were just trying to look for, with the current data that we do have, how we can implement, a machine learning model to kind of help out in this sense, but we haven't, because we don't have like a holistic DNS data collection, we haven't really looked at that approach. So we didn't go into that yet. Yes.
Hi, I was curious about how you're measuring the accuracy. Is it just the correctly classifying the positives, or also classifying the positives correctly and the negatives correctly?
It's both. So we did a tenfold cross validation, and we did it on the main things we were looking at was the accuracy, the false positive rate, and the false negative rate.
Is the data relatively balanced? Otherwise, if the data is almost all negative, then I can just predict negative and have very high.
Our data is pretty balanced. Like I said, we had about, for the domains, we had the million from the Alexa 1 million dump, and then we generated about that much from the 60 different malware mailings that we reverse engineered the DGAs for. So it was a balanced data set. Yes.
Could you talk a little bit about other machine learning projects like Capital One?
Sure. Before I do that, and I would love to get to that question, does anyone have anything relating to this before I jump on to other stuff? Oh, we do? Okay. I'll take one more and then I'll answer that.
Yes, what about obscure acronyms? For instance, something a data scientist at Capital One might look at is the website MISQP.com, Mixed Integer Sequential Quadratic Program, which actually can be used to facilitate some data science.
Yeah,
That looks
so
like gibberish, you know?
it does. And that's probably something that our DGA model would catch, but we do have whitelists in place. So we do for anything that like their first level domain is like, a lot of times we'll get like gibberish.amazon.aws.com. And so our DGA model would classify that as malicious just because of the gibberish in front of that first level domain. But we have whitelists in place for things like that we find aren't malicious, but our DGA model would catch. That's essentially how we handle it on a case-by-case basis.
Isn't the part that goes before something like Amazon.com, isn't that the second level domain? That's
Yeah.
under Amazon.com, so if you know Amazon.com is safe, anything before dot.
Right, so we do that, so we whitelist it because we are looking at the second level domain. But in your case, what you're saying with the data science acronym, our model would have detected that, but again, we have security analysts that are the ones investigating and putting the blocks in place, so they do often go and check the domains as well on like things like virus total, stuff like that. You can check whether a domain is rated as safe or not, so they do those checks before they actually put the blocks in place. And then if we want to move on, I can also just chat with you after this if you want to talk about other machine learning projects. Oh, you're good to know.